On a clear night, the stars look close enough to touch. They hang there, still, quiet, impossibly beautiful. And one of them is special. One of them has a planet orbiting it, a planet the right size, the right distance from its star, a planet that, on paper, could hold liquid water. We have dreamed about that world for decades. We have named it, studied it, written about it endlessly. We have even asked, could something live there? And then someone asked a different question. How long would it actually take to get there? The answer does not feel like a number. It feels like a sentence. On September 5th, 1977, we launched Voyager 1 from Cape Canaveral, Florida. It was built to explore Jupiter and Saturn, but it kept going. It has never stopped. As of today, Voyager 1 is the most distant human-made object in existence. It has been traveling for nearly 50 years without interruption. It is now so far from Earth that a radio signal takes over 22 hours to reach it. And that machine, that remarkable, tireless machine, is moving fast. It travels at roughly 61,000 kilometers per hour. That is faster than any bullet ever fired. 17 times faster than a rifle shot. To cross from one side of the United States to the other, Voyager 1 would need 4 minutes. So the question is reasonable. We have this machine. It is moving. It is heading outward. How long would it take to reach Proxima b? The closest known exoplanet to Earth, Proxima b, orbits a small dim star called Proxima Centauri. That star is our nearest stellar neighbor. It is the closest star to our own sun that exists. And by the scale of the universe, it is right next door, 4.2 light years away. In kilometers, that distance is 40 trillion. 40, followed by 12 zeros. We do not have a useful comparison for that number in everyday life, so let us build one. If you drove a car, non-stop, no sleep, no stops, at motorway speed toward that star, you would need 40 million years to arrive. Not 40,000, 40 million. The dinosaurs died out 66 million years ago. Driving to Proxima b would take more than half that span of time. Light itself covers that distance in 4.2 years. Light, traveling at nearly 1 billion kilometers per hour. Even light needs 4 years. Now consider what we have built. Here is where the number becomes something else entirely. At Voyager 1's speed of 61,000 kilometers per hour, directed straight toward Proxima b, the journey would take approximately 73,000 years. 73,000. Let that settle for a moment. The United States of America has existed for roughly 250 years. 73,000 years is 290 times that. Ancient Egypt, one of the oldest civilizations we know of, is around 5,000 years old. This journey is 14 ancient Egypts long. Modern human beings, people like you, people who speak, build, grieve, and love, have existed for roughly 300,000 years. This one journey covers almost a quarter of our entire species' history. You would board the spacecraft. Your children would be born on it. Their children would never know Earth. Their children's children would forget what a sky looks like. Generations would rise and fall in a metal room no larger than a house, traveling through a silence so absolute it has no comparison on Earth. 2,900 generations of human beings would live and die before the destination ever came into view. And we have not yet talked about what you would find when you arrived. Proxima b sits in what we call the habitable zone of its star. That phrase sounds promising. The word habitable does that to people. But the star that Proxima b orbits is not like our sun. It is a dim, red, deeply violent star. It erupts, not occasionally and constantly. Bursts of high-energy radiation pour from it in waves. The radiation reaching Proxima b is hundreds of times more intense than the radiation Earth receives from our own sun. Now picture you have survived 73,000 years of travel. You step out. Your ears would be among the first things to fail. Of the pressure environment around Proxima b, stripped of any protective layer by constant radiation assault, would not hold. Your eardrums, which are designed for the stable pressures of Earth, would rupture within moments. They are membranes thinner than a sheet of paper. They are not built for this. Next, your lungs. The tiny sacs inside your lungs that move oxygen into your blood, hundreds of millions of them, depend on a breathable atmosphere with the right pressure. On Proxima b, where the atmosphere likely cannot survive the star's constant radiation assault, there is nothing to breathe. The sacs collapse inward. The transfer stops. Your heart, already working harder as oxygen drops, begins to fail. It was built to push blood through a body that is breathing. Without oxygen, it has nothing to work with. It does not simply stop. So it struggles first. It accelerates. It fights, then it loses. Your eyes would fill with blood. The vessels behind your eyes, designed for a world with a stable sun, cannot withstand unfiltered high-energy radiation at this intensity. They rupture quietly. Vision fills with red. And then the organs deeper inside you begin to feel the damage that has been building since the moment you arrived. Radiation passes through skin, through muscle, through the walls of your stomach and intestines. It breaks apart the instructions inside each cell that tell it how to function. One by one, those instructions fail. There is no dramatic moment, no single thing that ends it. It is the slow collapse of every system that was built for a different world entirely. Now, here's the part that truly closes every door. You might ask, can we simply go faster? The answer is not a technology problem. It is a geometry problem. And here is the quiet trap buried inside the mathematics of rocket science. To go faster, you need more fuel, but more fuel means more weight on the spacecraft. The heavier the spacecraft becomes, the more fuel you need just to move the fuel itself. It builds on itself endlessly. More fuel, more mass, more fuel to carry the mass, more mass from the fuel. It is not a problem we can engineer our way around. And it is the shape of the mathematics itself. A closed loop with no exit. Every door you open leads back to the same room. And there is one more door still to close. You also need fuel to slow down. A spacecraft that cannot slow down cannot land. It cannot orbit. It flies straight through and continues into nothing. So the fuel required to stop at the destination is equal to, and in many cases greater than, the fuel required to get there. The mathematics of this does not bend. It creates a loop where every solution demands more than the last solution can provide. Physics, not cruelty, not failure, is the trap. The geometry of interstellar travel is not a wall we are approaching. It is a wall we have already hit. Not because we haven't tried hard enough, because the shape of the mathematics leaves no door open. There is no upward path out of this. There is only the number, 73,000 years. Sitting quietly at the end of every calculation. But we have not simply theorized about this. We have sent real machines into the dark, and the results have been instructive. In December 1995, NASA sent a probe into the atmosphere of Jupiter, the largest planet in our solar system. The probe was called Galileo. It did not enter the most dangerous region of Jupiter's atmosphere. It entered a relatively calm part. 58 minutes. That is how long it lasted. 58 minutes in the calm part. Then the pressure, building slowly, invisibly, crushed it completely. No signal, no warning, just silence. 58 minutes in the calm zone of a planet we already know well. Think about what the more violent zones would have done. Think about what 73,000 years of interstellar space would do. On December 24, 2024, NASA's Parker Solar Probe made its closest ever pass of the Sun. It had been launched on August 12, 2018, with a single purpose: to reach speeds no human-made object had ever reached before. On that Christmas Eve approach, it was traveling at 692,000 kilometers per hour. That is the fastest any human-made object has ever moved in the history of our species. At that speed, the absolute peak of everything we have ever built and launched, a journey to Proxima B would still take approximately 6,600 years. Longer than all of recorded human history. Longer than the time from ancient Mesopotamia to this moment. Our fastest machine, our greatest achievement in speed, 6,600 years. And it never slows down, never stops, and never arrives anywhere it can land. And Voyager 1, the machine we actually sent outward, is 11 times slower than that. 61,000 kilometers per hour, 40 trillion kilometers to travel, 73,000 years to arrive. 6,600 years even at our absolute fastest. Radiation hundreds of times stronger than Earth's. No confirmed atmosphere. Endless stellar eruptions. A planet locked permanently. One face in scorching light, one face in permanent night. Thousands of generations who would never see the destination. Gone. There is a version of this story where we feel frustrated, where the distance feels like a problem waiting to be solved. But perhaps the more honest reading is something quieter. We are not being held back by a lack of ambition. We are standing at the true edge of what physics allows. and finding that the universe simply is not designed for us to cross it easily. Proxima Centauri has been burning for nearly 5 billion years, long before the first living thing moved on this planet, long before the first human mind ever looked up and wondered. It did not pause for any of that. It will not pause after we are gone. We built a machine in 1977. We gave it everything we had. We launched it into the silence. And today, nearly 50 years later, it is still traveling, still moving through the dark, not yet even close. But the star we dream about is still 40 trillion kilometers away, and the universe holds that distance like it holds everything else, without effort, without apology. I hope you found this as humbling as I do.